All right, now let's solve our combustion thermodynamic problem part 2. So I know I talked about this in the last video, but it comes up again. So I'm going to do this one more time in case you didn't watch the first one. So the analogy, or the, piece of the problem that we're going to be using in this harder combustion problem uses this concept. So if I have a 1,000 calorie bag of cookie and I have 100 calories per cookie, how many cookies do I have? It's going to be 10 cookies, right? If we have 1,000 calories, we divide that by 100 calories per cookie to get our 10 cookies. So that was pretty easy, but we're going to do the exact same thing in this much harder problem. We're going to be able to find the amount of heat that we need. We're going to be able to find the amount of heat per canister, and we're going to be able to use this to solve for the number of canisters that we need. All right, take a moment and see if you can think about how to start this problem. Get going on it if you can, and come back if you get stuck. So let's consider some things. First off, the minimum number means that everything is going perfect. We're assuming that all the heat transfer is perfect here, and that's okay. We also have we have combustion going on. It says burning, but burning is the same thing as combustion. And we know that combustion is when we react a hydrocarbon with oxygen to form carbon dioxide and water. And then, of course, whenever we have grams, and we also know the species, we also have moles there. So let's make a plan. We're going to take our kilograms of our hydrocarbon, convert that into moles of our hydrocarbon. Now we can use as moles of our hydrocarbon and our DH of reaction to solve for our kilojoules of heat total. Right? So this is going to tell us the amount of heat we have inside our canister. We also know how much water we need to heat. So if we have our kilograms of water, we can figure out our heat to boiling each day because we know Q equals MC delta T. We'll calculate that heat. So that's going to tell us our heat needed per day, which we can multiply by 5 to know our total heat needed over the course of the day. So we'll have our kilojoules per heat in each of our canisters, our kilojoules of heat that we need total over the course of the whole week, and we can take our total energy needed over our total energy per canister to get our canisters needed. So that's going to be our plan. If you think you can do it, pause here, try to do it on your own, and come back when you need help. All right, let's start with our kilojoules of heat total per canister. We know that each one has 100 grams. We know our molar mass, and so we can take our molar mass, we can use this to find moles. Now, using this and DH, we can solve for our heat per canister. So we need to write out our combustion reaction. We know that it's a hydrocarbon plus oxygen goes to carbon dioxide and water. But we also need to balance it, right? So we have 3 carbons, so we're going to need to add a 3 in front of the carbon dioxide. We got 8 hydrogens here and only 2 here, so we're going to need to add a 4 out front. That's going to give us 10 oxygens on this side, so we'll need a 5 over here. From there, we can fill into DH, making sure to grab the gaseous water for here, our carbon dioxide. Our oxygen is going to be 0. We don't need to look that up. We know that that's 0 because it's a diatomic gas in its standard state. And then we can fill in for our C3H8. We type this all into our calculator to get our answer. But remember that this is kilojoules. This is the kilojoules for 1 mole, however much the stoichiometry out here is, 1 mole. So we need to multiply by our number of moles, which we found up here, to get our total kilojoules per can. All right, next up, now we need to figure out how much we have in a day, how much we need in a day, I should say. So we're going to use Q equals MC delta T for that. So this is another good place to pause, try to do it on your own, and then come back and see how you did. So we can fill in our 2 kilograms. I filled it in grams here. You could also go ahead and leave it in kilograms and write the conversion factor here. See that it's going to cancel, kind of like we did on the first part. I'm just doing it a slightly different way this time to show you a couple of different ways to do this because it's so similar. We fill in our specific heat. We fill in our delta T, and we get our answer. I converted into kilojoules here just because our delta H is in kilojoules and it's much more manageable to look at this number than using it in joules. Now keep in mind this is per day, so that's not going to be how much we need over the whole trip because we're going to be gone for 5 days. So we then need to multiply this by 5 in order to get how much we're going to need for our week of camping. All right, so now we know how much energy per canister we have. We know how much we need for the entire week of camping. Now we can do our last step. Another good pause point to see if you know what you're doing. Come back if you need help. So we can have our kilojoules per can. We know how many kilojoules total is needed. Remember that this is going to go into the water, so when you're doing this, you would go ahead and flip that back to a positive. And we can fill in our total needed over the course of the whole week per can. This is going to give us cans on top, so that also double checks to make sure that we're doing this correctly because our units match. And then that's going to give us less than 1 canister. So we can't bring less than 1 canister, so we would need 1 canister in order to do this one. And that is how you do this problem.